everyone, I'm Dr. Rizwana, working as a Professor of Physics in Institute of Aeronautical Engineering. Today I'm going to do some numerical problems on simple harmonic oscillator. So already I made some videos on different types of simple harmonic oscillator. We have discussed about of course mechanical simple harmonic oscillator as well as electrical harmonic oscillator. And then we have discussed about both simple and of course we have discussed about both mechanical and electrical damped harmonic oscillator as well as electrical harmonic oscillator. This is forced harmonic oscillator. So we have taken simple, damped as well as forced harmonic oscillator. And we know that what are harmonic oscillators? These oscillators, they will retrace their path again and again during their motion. And here we know that these harmonic oscillators, they are subjected to different types of forces. So if it's a simple harmonic oscillator, then a restoring force will act on it in order to bring it back to its original position. And whereas if we take damped harmonic oscillator, in addition to restoring force, there will be some frictional forces acting on the oscillator in order to dampen its vibrations more faster compared to simple harmonic oscillator. Whereas in case of forced harmonic oscillator, so here in this case, what we'll do in order to sustain oscillations, in order to see that oscillations won't get damped, we are going to apply external force. And here this oscillator at one particular point, it will start vibrating with frequency of external force. So this is just to maintain the oscillations of vibrations of a particular harmonic oscillator. So today we are going to do some problems based on these three types of harmonic oscillators: simple, damped as well as forced harmonic oscillator. So moving further, coming to our first problem. Here what is given? A particle, it is executing simple harmonic motion. And what is the time period? Time period is 10 seconds. And here we were given amplitude. Amplitude is around 1.5 meters. And we were asked to calculate its maximum acceleration and velocity. So we know that if omega is the angular velocity, then how this angular velocity and time period are related? The relation it is given as time period is equal to angle described in one revolution divided by, so here generally, how we'll write our angular velocity? Angular velocity omega, it is given as angle that is described in one revolution divided by time taken to complete one revolution. And we know that what angle will be described in order to make one complete revolution, it is equal to 2 pi by time period t. And from this we have of course we have our time period as 2 pi by omega. But in our case, here we were given time period value and we were asked to find a maximum acceleration and velocity. So from this value of time period, first we'll try to find angular velocity. So time period is 2 pi by omega, then obviously angular velocity will be 2 pi by time period t. And our time period t, it is given as 10 seconds. So if we substitute, we get our angular velocity as 0.628 radian per second. So once we know angular velocity value, then we can find values of maximum acceleration as well as maximum velocity. But what is the expression for velocity associated with simple harmonic oscillator? It is omega times square root of amplitude square minus displacement square. But we were talking about maximum value of velocity, and here for maximum value of velocity, we'll take our x to be 0. So in that case, velocity value, it comes out to be, so here velocity maximum value, it comes out to be product of amplitude into angular velocity. And what is the amplitude? Here it is given. So here amplitude is of course 1.5. And what is the value of angular velocity? 0.628. If we do it, then we have our maximum velocity as 0.942 meters per second. And similarly, what is the value of maximum acceleration? It is given as omega square x. Acceleration is maximum if displacement is a. That is nothing but amplitude. So here we are going to substitute value of angular velocity as well as amplitude. If we do it, then our maximum acceleration, it comes out to be 0.59 meter per second square. Then coming to second problem, here in this case, we were given velocity which is 16 centimeter per second. And we are saying that this particular body is passing through its center mean position. When it is passing from its center to from the center mean position, when it is vibrating, then its velocity is 16 centimeter per second. And we are saying that it goes 1 centimeter on either side of mean position, and we were asked to find time period. So what is the velocity given? Velocity is 16 centimeter per second, but what is the formula for velocity? Omega, which is angular velocity, square root of a square minus x square. A is amplitude and x is displacement. And here in this case, when it is at mean position, that is at the center position, then displacement will be 0. So here we are talking about the pendulum. First pendulum, this is our mean position. So at mean position, displacement is 0. So if I substitute x to be 0, then here, of course, when it is at the mean position, here velocity is 16 centimeter per second and amplitude is 2 centimeters because it is moving 1 centimeter on either side of mean position. So here, what is the amplitude? So it is going and then coming. So that's why 1 centimeter, 1 centimeter. So amplitude will be 2 centimeter. So maximum distance covered. So it is equal to 2 centimeter. And here we know that from this formula, we know value of velocity which is 16 centimeter per second. Omega value, we are putting it as it is. We know amplitude which is 2. From this, we are going to get value of angular velocity which is 8 radian per second. And we have to calculate its time period, and we know the time period is given as 2 pi by omega. So 2 into 2.14 divided by omega is 8. Then our time period, it comes out to be 0.785 seconds. Then here in this problem, we are talking about damped harmonic oscillator. What is damped harmonic oscillator? Damped harmonic oscillator, what we'll do, one good example in order to explain damped harmonic oscillator is we have a spring and mass arrangement. And in the spring and mass arrangement, what we have done, this mass we are inserting in a liquid, okay, highly viscous liquid. Then what happens, this mass, it will be subjected to frictional force which is exerted by liquid, and that will try to dampen its vibrations. So here, if we have such damped harmonic oscillator, and what is the mass of the body which is hanging to spring, it is taken as 5 grams. And here we are saying that what is the restoring force or elastic force? It is given as 40 dyne per centimeter. And we know that in case of damped harmonic oscillator, there are 2 forces acting on it. One is restoring force, and then other one is frictional force. So here, the elastic force, that is nothing but restoring force value is given, and frictional force value is also given, 5 dyne second per centimeter. And it is, like here, we were given its displacement. If it is displaced through 2 centimeter and then released, find whether the resulting motion is oscillatory or not. And also we have to find time period if it is oscillatory. We know that if we take damped harmonic motion, there are 3 cases. First one is underdamped oscillation, and then we have critically damped oscillation, and then we have O-damped oscillation, right? And restoring force, if we take, it is given as minus kx, and if we take frictional force, it is given as minus r dx by dt. K is force constant and R is frictional force constant. And if we try to get equation of motion, so this is the form of equation of motion for damped harmonic oscillator. But what is 2B? 2B is R by M. R is frictional force constant, M is mass, and here omega square, frequency of oscillation of the body, it is given as ratio of force constant to the mass. And here, when we are talking about these 3 cases, when we call a particular motion to be underdamped, in this case, B square will be less than omega square. And when we call it as critically damped, when B square is equal to omega square. And when we call it as O damped, when B square is very much greater than omega square. So here, our oscillator, it will be in motion only if it is in underdamped stage. And in underdamped stage, here B square value should be greater than omega square. So in order to find whether the resulting motion is oscillatory or not, I have to check whether this B square value is less than omega square. And if it is oscillatory, then we need to find what is the time period. So here, from the data given, mass is given 5 grams. Elastic force is given, that is nothing but K value, which is 40 dynes per centimeter. Frictional force constant value is also given, which is 5 dynes second per centimeter. Displacement value is given. Now, what I am going to do, I am going to find B value and omega square value. So here, so that is nothing but, as I told you, we have to go for underdamped motion. So B square less than omega square, we need to find this. So we know that 2B is equal to R by M. So what is the value of B? B is R by 2M. R is 5 divided by 2 into what is the mass? Mass is 5 grams. So B value comes out to be 0.5 and B square value is 0.25. Now, in order to find omega square, frequency of oscillation, which is given as K by M, and force constant is given as 40 and mass is given as 5. If you do it, it comes out to be 8. So obviously, if we compare B square value and omega square value, so B square value is less than omega square. That's why our motion is oscillatory. And if motion is oscillatory, in case of undamped motion, how time period is given? It is not just simply 2 pi by omega, but it is given as 2 pi times, like a 2 pi divided by square root of omega square minus b square. And we know value of omega square and b square. If we substitute, then time period, it comes out to be 2.26 seconds. Then coming to fourth problem, here we are talking about forced harmonic oscillator. And if we take forced harmonic oscillator, compared to damped harmonic oscillator, there is one external force being applied to particular body. And here we have restoring force and then we have frictional force. Apart from frictional force, we are going to have external force, which is given as F is equal to F naught sin Pt. F naught is magnitude of external force and P is frequency of external force. And data given is mass is 0.5 kilograms. And here we have given linear spring whose force constant value is 1000 Newton per meter. And damping coefficient, that is R value is 0.05 Newton second per meter. Okay, so here meter inverse is given and external force formula is there, and here this is the formula for external force. We were given magnitude of force, which is equal to 25 Newton, and what we are supposed to find, and one more point is given here, frequency of external force, which is P, it is twice the natural frequency of system. So here P, it is equal to 2 omega. So we need to find omega. So once we know omega, then it will be easy for us to find the amplitude of resulting motion as well as phase shift of displacement with respect to driving force. And what is in case of forced harmonic oscillator, amplitude, it is given like this. Here in this case, F. What is F? F is nothing but magnitude of applied force, which is F naught divided by mass. So F naught by M will give us small f value divided by square root of omega square minus p square whole square plus 4b square p square. What is omega square? It is natural frequency of oscillation of the body, and p is the frequency of external applied force, and b is damping coefficient, which is given by 2b is equal to r by m. Okay, and of course phase shift tan theta is 2bp by omega square minus p square. So first we'll try to find small f value, which is magnitude of external force by mass, and here we were given magnitude of external force as 25 Newton and mass is 0.5 kilograms. So if we do it, then this is the value of small f, and first we'll find omega square. Omega square is k by m. So here k is force constant, which is 1000 divided by mass is 0.5. So it comes out to be 2000, and 2b value. So in order to find b, so first we'll find 2b by taking ratio of frictional force constant to the mass. If you do it, it comes out to be 0.1. And how to find p-value? It is given twice the natural frequency of oscillation. So we know value of omega square. So obviously omega will be square root of 2000. So it comes out to be 89.4. So once we know all these values, we can find amplitude as using this formula. What was the formula for amplitude? Amplitude is given by f by square root of omega square minus p square plus 4 bp. So here 4b square p square. Sorry. So it is 4b square p square. We know value of f, omega square, p. Also we know 2b value. So once we substitute our amplitude, it comes out to be 8.34 millimeters. Then coming to phase shifter. Formula is 2b p by omega square minus p square. So 2b value is 0.1 and driving frequency is 89.7 divided by we know value of omega square as well as p square. Then our phase shift is, it comes out to be 0.853. Then coming to last problem. Here also we are talking about simple harmonic oscillator, and we were given here in this case velocity at the mean position. So velocity of simple harmonic oscillator at the mean position is 1 meter per second, and acceleration at one of the extremities is 1.57 meter per second square, and we need to find time period of vibration. Now for that, first what I am going to do, I am going to take ratio of maximum acceleration by maximum velocity. And we know that value of maximum velocity is a omega. How we got this? We know expression for velocity as omega square root of a square minus x square, and it will have maximum value when x is equal to 0. So at x is equal to 0, velocity will be maximum, and if I take that maximum value, it comes out to be a omega. And when we are talking about maximum value of acceleration, so acceleration, it is given as minus omega square x, and at x amplitude, when we consider our amplitude as x is equal to a, our acceleration will be maximum. And what is that maximum value? Minus omega square a. So if I am going to substitute this value in this ratio, I end up having my angular velocity omega as ratio of maximum value of acceleration to the maximum value of velocity. And we were given both these values in our problem. So if we do it, angular velocity comes out to be 1.57. Then obviously time period will be 2 pi by omega. If we substitute, it comes out to be 4 seconds. So we have done various problems on various harmonic oscillators. We have covered simple harmonic oscillator, damped harmonic oscillator, as well as forced harmonic oscillator. So with this, we are going to end our session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.